Okay, chapter 14a, motion in a straight line. Example 5. A body moving in a straight line with uniform acceleration. Initial velocity is 12 meters per second. The body stops after 20 meters. Find A. There are actually multiple ways of solving this question. Even though it's a simple question, we do have choices. Now, if you're a physics student, you've got those lovely physics equations you can use for uniform acceleration. They are not on the specialist formula sheet, but if you are familiar with them and you know them, you could potentially use them. Well, I'm going to go keep it purely math and go a different way for where we're going to go. So I'm not relying on those physics equations. Now, I know that acceleration is uniform. So I'm just going to use K being a constant, and that's my acceleration. I'm given multiple information. Now there's a few ways I can go with this. I'm going to go with that acceleration is v dv dx. That's on your rule sheet. Now I chose that because we're talking about a distance as well, so I thought, oh, that could be good. So v dv equals k dx. Integrate both. I get v squared on 2 equals kx plus c. I need to find c. Now if we talk initially, v equals 0, initially, we're told v equals 12 meters per second, and I'm going to assume my initial position is 0. I'm going to call it 0. So then I've got 12 squared on 2 equals k times 0 plus c. 72 is c. So I have v squared on 2 equals kx plus 72. I'm told if the body stops after 20 meters, find A. So we're going to go if the body stops after 20 meters, that's v equals 0, x equals 20. So of course that's going to be 0 squared on 2, k times 20 plus 72. And it's an easy solve for k, isn't it? K is going to equal negative 72 over 20. Simplify that down, it'll be negative 18 over 5. So acceleration is negative 18 on 5 meters per second squared. And that's a really nice solution to that question, to go that way. But we know that sometimes when we're doing this, especially if you're in an exam, your brain might go different ways. So if you started with A equals K, and you went straight to the good old dv/dt equals k. So then dv equals k dt, integrate both sides, v equals kt plus c. This is a nice standard way we like to go. Now initially, t equals 0, v equals 12. That's nice. So 12 equals k0 plus c. In this case, c is equaling 12. So v equals kt plus 12. And then this is where we run a little bit aground, because we get to that point, but to find the body stops after 20 meters. So the velocity is 0 when x is 20 meters. No mention of time. So choosing this way to go is a little bit more difficult, but you still can follow this path. If we do this, I'll just go down here and I'll go now to a position. So that'll be kt squared on 2, plus 12t plus c. Now if we want to find c in this case, when t is 0, r is 0, so therefore c will be 0. So r will be kt squared on 2 plus 12t. And this way you then go, okay, I've got these two equations. I know that when I know that at the start, when t is 0, v is 12. So that's pretty cool for me. But I don't know where I'm going from there. Okay. So v is 12 and t is 0. So we go down here and we go, okay, when our position is 20, we get kt squared on 2 plus 12t. We don't know what t is. Now if I go back to my velocity, if I'm going to go, let's call this a t1, because that's where we want to find. If I go when v is 0, when t is t1 plus 12, then I get t1 is negative 12 on k. And I'm going to substitute that in down here. T1 just indicating that that's that particular time when the velocity is 0 and the distance is 20. If we substitute it in, we get k over 2 times negative 12 on k squared plus 12, negative 12 on k. 20 gives me, this will simplify to 72 on k minus 144 on k. 20 on negative 72 on k, of course, is going to give me k negative 72 on 20, which is negative 18 on 5. We get the same answer. So while it is possible to do it that way, it's a little bit trickier, a little bit more complicated, but you get the same answer. If you know your physics rules, they are an option to use. If not, I would probably suggest method 1, using our acceleration as v dv dx. That's example 5.